All right, so we start out here with this section of notes with our emphasis on our atomic structure, which will help lead to chemical bonding. Now, a lot of this serves as review for those that have had a chemistry class before, and so I want to present this in a little bit different light and highlight some things along the way that need to be emphasized. Okay, so number one here, we have some important statements in chemistry and in science in general. Number one, all matter is composed of atoms. All right, atoms are the building blocks of chemistry and anything that we deal with here in this particular physical world. Okay, and so we have Dalton's atomic theory. And this is an important atomic theory because in the 1800s here, this is the first time where Dalton or any scientist is saying, okay, specifically, this is what our stuff is composed of. And Dalton made a few things, and he made some assumptions here that actually turned out to be true. So Dalton said elements are composed of atoms. All right, that's the simplest building block here. He said that all atoms of an element are identical. Now, this statement here was actually proven false because we have the items known as isotopes. Okay. He also said in chemical reactions, chemicals and atoms break apart, bonds break apart, atoms rearrange, reconnect together in a different way, and they form those different types of atoms. Now, we simply know that as reactants and products. He also made a very, very important point and said, hey, in a chemical reactions, atoms are neither created or destroyed. And then he said that compounds are going to form when elements are going to be combined, and we eventually called that a chemical combination in the form of a chemical bond. Okay, and we have some important things here. We have to remember Dalton, why so many of these things, besides that isotope business, was important, was because he had experimental data to say, hey, this is why and this is what's happening. Took a lot of good, careful measurements. All right, it's really important that you understand and know Dalton's atomic theory. Okay. Now we get to this. All right, an atom. We've seen this before. You've heard of this before. But an atom is composed of three subatomic pieces or particles. You have the proton, the neutron, and the electron. Protons have a positive charge. Electrons have a negative charge. And that neutron has a neutral charge, okay? The other thing here is this. We have this absolute charge. Now, traditionally, we're used to seeing a proton written as a positive 1 and a electron written as a negative 1. The reason that they have that, if you look at the electrical charge, really we could say absolute electrical charge in this particular first chart, but you have this charges here, which can actually physically be calculated. And notice there that times 10 to the negative 19 number, that's a pretty small charge. Well, you have to remember protons and electrons are really, really small, right? The atom is so microscopic, we can hardly see it even with really, really quality material or quality instruments. And so an even smaller part is even more difficult to find and look at and measure, okay? Then our mass, okay? Protons and neutrons are going to make up a majority of our mass. And you can see the specific mass has very, very extensive details or decimals, but we simply call it 1 AMU. Protons and neutrons, 1 AMU. An electron Yeah, even though it has a -1 charge, it's still matter. So it's going to have some mass, but that's a really, really small mass. All right. And just a note there, AMU is atomic mass unit. It's just the measurement they use to measure these really, really small particles. Okay. Now, we have seen that before. And so the questions that should come up here is this. And this should be at the end of your first page. Where are subatomic particles located in a particular atom? All right. And so we're going to start here and we are going to break apart. We are going to break apart this particular picture of our atoms. The first thing that I want to write down is this. Experiments have shown that protons and neutrons are located in the nucleus and electrons are located outside the nucleus. Okay, so let me take a moment to write that information down. All right, that's really great. But let's build a visual picture. I like to see things here rather than just write these things down. Okay. And so if we have this, all right, I'm going to draw my picture right under what I just wrote down in purple there. We're going to have this. I'm going to draw a really, really tiny dot. You might not be even able to see it there. Okay. So there's my dot. And then I am going to have this. I'm going to use my symbol terminology here, and my dot didn't even show up. There it is. Then we're going to have this. All right. Now, I want to highlight a couple of different things. All right. So right here in the center, okay, right here in the center, this right here, that dot, that tiny dot, that is our nucleus, okay? And we're going to get back to this, okay, because I want to talk more and more about the nucleus and about the other parts, but I want to make a couple of unique points, okay? The first point that I want to make is that this right here is our first picture of the atom, okay? And we're going to call this Bohr's model of the atom because we're going to get into his specific model. So this right here is our first model of the atom. Okay, first picture. Now, another thing that I want to emphasize here is that I can't show it on the picture. I don't have that good of drawing ability, but atoms are spherical in shape. And so we're just going to simply put atoms are spheres. Okay. Now, I want to get back to my nucleus point. The nucleus is going to contain protons and neutrons and most of the mass of the entire atom. All right? So I'm going to add to this different definition here. The nucleus contains protons and neutrons And protons and neutrons in that center, right, the nucleus. And that center, that small little dot is going to contain most of the mass. So it's a really, really dense region in there. Now, I want to emphasize the point about volume, okay? Most of the mass in that really tiny dot, our volume is going to be composed mostly of our electrons, okay? So most of the volume of the atoms come from the electrons. Now, I also want to take the time right here to talk about our perspective. And really, it's a size perspective here. And that is this, okay? We want to ask ourselves this following question, okay? And I will use, let's use dark orange there. That'll look nice. We want to ask ourselves this, okay? Is this picture of the atom really drawn to scale, okay? Well, let's put this in perspective. I'm going to maintain that orange color here. If I take a really, really fine sharpened drawn pencil, and I can't do this on the electronic board, but if I take the really sharpened drawn out pencil and you take that and you put a dot, okay? Now, that dot's probably even bigger than what we would have with a pencil, but we could say this, that this dot right here that I just drew, this dot is the smallest dot that you could draw, and we're going to represent this as our nucleus, that contains just one proton. Based on that size of that dot, that really, really dot, which probably doesn't even show up on that screen, but it's there, okay? So really tiny pencil dot. If you were to have that pencil dot as the nucleus, the closest electron would be almost 10 feet away, all right? So again, if we drew this to scale, we would have to go way past this whiteboard here, and we would have to say, okay, that dot, if that's the size of our nucleus, the electron would have to be more than 10 feet away, okay? Mind blowing right there of how small the atom is and how small the pieces, the protons, neutrons, and electrons are of an atom, right? So that gives us a really good picture of our particular atomic structure, all right? We will continue moving on with this, all right? So now we go through this and we say, all right, let's talk and let's learn a little bit about our nucleus, right? We said it's right there at the center in our picture, and it's going to contain our protons and our neutrons and most of the mass, all right? The tiny little area is going to contain most of our particular mass, all right? With this, because there's such a small area, that little tiny area, with most of the mass of the atom, the density is going to be enormously large. Like, it's almost mind-blowing how large that density would be, Now, we put this really simply here. The designers of the periodic table actually did a really, really good job. And if we pull out a periodic table here and we look for these things, the number of protons is going to equal our atomic number, which is going to be our big whole number, okay? Now, until I tell you otherwise here in this unit, your number of protons is equal to your number of electrons. Not always the case, but in this section here, I do want to keep that fairly simple. All right, so let's put this test. Let's put this knowledge that we've learned here to the test and just review some information off of the periodic table. All right, where do we find the atomic number? Well, periodic table, and I want to add just a little bit of info to this, okay? Specifically, it is going to be the whole number on each element's box, okay? The whole number, okay? Now, there's some elements that have an atomic mass of our a whole number, but these atomic masses here, typically at the top of the box here, we'll point out some examples, all right? Atomic number of carbon. Well, if we find carbon, the element is C, in case you forgot there, element C there, or carbon. We find carbon on the periodic table, and the atomic number is 6. Now, what that means is that in our particular atom here, there are 6 protons. The atomic number represents the number of protons. What I just told you on the previous slide was that the number of protons and electrons are equal for a neutrally charged atom. And until I tell you otherwise, all of these will be neutrally charged. Okay? Now, plutonium. Plutonium, if we look plutonium up here, it is going to have the symbol Pu. And plutonium, the whole number that's listed, now the molar mass is actually listed as a whole number, but the whole number, the atomic number that is listed for plutonium is 94, which means we have 94 protons. And because it's neutrally charged, no charge, we have 94 electrons. So the point of this is to emphasize that our particular atomic number is equal to the number of protons, and because we have a neutrally charged atom, it is equal to the number of electrons. Now, I did not mention the number of neutrons. Okay, you got to do a little calculations to get to the number of neutrons. We actually need a little bit more information, but number of protons is equal to that atomic number found on that periodic table. All right. So now we get into this, and we want to keep diving in and talk about our atomic structure, right? We have a good picture. We have identified what makes up most of the mass, protons, neutrons, where items are, protons, neutrons, in that nucleus, where electrons are on the outside of that nucleus. And now we need to do this. All we have said about the electron is we said, hey, it's outside the nucleus somewhere. But we need to identify more specifically where this particular electron could be. Okay, so now we need to take a picture of our atom. All right, so Bohr. Bohr is probably one of the founders on atomic structure. Really did a lot of groundwork for what we have here. All right, so we have our picture. Bohr noticed a couple of things, and he did through experiments. Number one here, if we were to, I'm going to use orange again, draw that really tiny dot there, right there in the center, barely even shows up. That really tiny dot there is going to be our nucleus. So right here, this thing right here is our nucleus. Then Bohr, with his work, all right, won a Nobel Prize for this type of work here. A lot of math goes with it. he noticed this. They had electrons were in these specific orbits, all right? And so we're simply going to call this each rung an energy level and an orbit. So this first rung or this first ring is our first orbit. It is also the first energy level. Okay? The second ring is our second orbit, or the second energy level. And this third ring, we only have 3 rings here for this picture. We can have more. This third ring is the third orbit, or the third energy level. Now, I want to talk about this in terms of energy, all right? The first energy level is going to have the lowest amount of energy, okay? I don't have a whole lot of room to write here, but our first energy level here, I'm going to use the color red. This right here, our first orbit, okay, is going to have the lowest energy level, or is going to be the lowest energy level. Then second energy level, we're going to get just a little bit higher or increased amount of energy. Our third energy level in this picture is going to have an even higher energy level still. So my point with this is that as you increase your orbit, or as you increase your energy level, you are increasing, or you are gaining more and more energy. You are having higher and higher levels of our particular energy, okay? So we keep moving through all of this, and we get to some very, very important points with that model, with Bohr's model in mind. So number 1, it says the electrons are in orbits around our nucleus, okay? Now, prior to this, the electrons could be anywhere in the nucleus, okay? So prior to what Bohr said, it could be anywhere in the nucleus. All right, I'm going to get the notes fired back up. All right, so again, subpoint to number 1 is that prior to this, the electron, which I'm going to abbreviate just as e to the minus here, going to abbreviate just as e to our minus, is going to be, could have been anywhere in the outside the nucleus. All right, let's get back on track here. Okay, so number one, once again, our subpoint to this here, electrons had to be in these orbits. Prior to this, the electron, which I'm going to abbreviate as e to the minus, could be anywhere outside the nucleus. Now the electron has to be in an orbit. Okay. Next thing, Bohr realized that the energy of the electron was very important in explaining some of the behaviors of an atom. Each orbit has a very specific amount of energy associated with it. This was a very important realization, that an electron can only have certain allowed energy, and we refer to these amounts of energy as the energy levels. Okay. Again, prior to this, the electron could be anywhere outside the nucleus, which means the electron could have any amount of energy. Okay, so let me write that down. The other point I want to make with this is that the electron now has to have a specific amount of energy because it's in a specific energy level. All right, so we make two really good points and some subpoints here. Now, I want to keep going on with this information, and I want to continue talking about some other points from Bohr. Now, we don't have to have any subpoints for number 3, which is good. But number 3 says the electrons closest to the nucleus are lowest in energy. Lower the energy, the better, the happier, however you want to view that. And then number 4, the maximum number of electrons from Bohr's model, the maximum number of electrons an energy level can have is given by the formula 2n squared, where n is the energy level. All right, so let's go ahead and identify how many electrons could be in a particular energy level. All right, so I'm going to kind of make a chart here. I'm going to have my energy level, and Going to give some space here. I'm going to have that formula 2n squared. Okay. Now, with this formula here, we have our first energy level, and that is n equal 1. The second energy level, our n, is going to equal 2. Third energy level, our n equals 3. And for this, we'll stop at our fourth energy level. N is going to equal 4. Okay? 2n squared, right? If we put our value for n in this formula, we would have 2 times 1, and 1 is being squared. Well, 1 squared is still 1. And so we get in the first energy level 2 electrons that can maximum be in the energy level, the first energy level. Now, we go to the second energy level. 2 times 2 squared. Well, 2 squared is 4. 4 times 2 is 8. So 8 electrons is the max electrons in second energy level. Okay. We go to our third energy level. So 2 times 3 squared. Okay, 3 squared is 9. Times 2 is 18. So 18 electrons is the max number of electrons in our particular third energy level. And then for our class here, we end with this. Fourth energy level here, we have, again, still use the formula 2 times 4 squared. Well, 4 squared is 16. 16 times 2 is 32. 32 electrons is the max electrons in that fourth energy level. Now, I want to make a really important point here, and that is this, that each energy level can hold a different number of electrons. Okay, that's a really important point. Now, I'm going to do a really similar thing for number 5. I'm actually going to copy and paste this business on the energy level, and I'm going to put it right below here. Okay, so our energy level right there, energy level here, and then let's see, just going to move that over. Oh, no, that will work just great. Okay, we have this. I'm going to write it in red here. Okay, we can predict our radius, right? We don't need to worry about this a sub 0, that Bohr constant. We can get a pretty good idea of our radius. So on this side here, I'm just going to say r equals n squared times that a, and we call that sub 0, okay, just Bohr's constant. And so we can get a pretty good idea of our radius. So for the first energy level, we could get 1 squared times a sub 0, which we really don't need to worry about a sub 0. But that first energy level would get us a radius of 1 a sub 0. Our radius of the second energy level, we would have 2 squared times that a sub 0, and we would get 4 a sub 0. Our third energy level, we would get 3 squared times that a sub 0, so that'd get us 9 a sub 0. And then our fourth energy level, that's all we're going to worry about today, we would get 4 squared times a sub 0, which would be 16. Now, I want you to notice that this gets bigger, and it gets bigger on an exponential basis, all right? So we're going to break these notes into another part here. All right, but this is a good stopping point for right now.